All right, welcome to our weekly webinar. Today we have Robin Vismata with us, and the conversation is going to be on creating and running virtual laboratory courses here today. And he's also going to be giving a demo. So thanks for being with us here today, Robin.
Thank you for the invitation. So I will now start my presentation. So you should now see it. It's loading. Okay. Okay. So okay. So thank you again for the invitation. And as you mentioned, I will be talking about our experience. I'm talking for myself and for Olinda Isabella, which is also here, which was the lead on this project. I'll be talking about our experience on creating and running virtual laboratory courses. So before I start, a bit of background about myself, because it's also the first time I'm joining this webinar. I'm part of the Photovoltaics Materials and Devices group, which you see the logo here on the bottom left of the slide, which is part of the EMCS faculty. And I've been there for a few years now because I've carried out my PhD over there. And for the last couple of years, I've been a postdoc there, and I actually worked mostly on developing courses for online education, so mostly ProFeds, but also for on-campus education since last year. So during this webinar, I'll be discussing our experience, as I said. So I first start by introducing what problems we faced, mostly since 1 year or so because of the pandemic, and which solutions we found in terms of the virtual online courses. And then I will go through what was our experience in the creation. So I will start with a preliminary phase, so what we needed to start with. Then I will describe briefly the development and the final phase. And then probably the most interesting part will come after that, when I'll give a short demo of our virtual course. And to conclude, I will give a short list of lessons that we learned while creating and running this course. So to begin with, the first problem that we observe since last year has been, of course, the pandemic, because this is our laboratory, which at this time of the year, or at this time last year, should have been full of students carrying out the course, our photovoltaic laboratory course. However, this is the situation. The laboratory is empty and no student is there. And of course, this is unfortunate, mostly for our students that require maybe to carry out this course in their program and couldn't because of the pandemic. However, for us, this was not always the problem, or not the only problem, because for many years, also before the pandemic, we had a problem of demand and offer. And in particular, this course has a limited amount of places available because of laboratory is relatively small. And always the demand of students to take this course was quite higher. And in particular, for our course, we could offer maximum to 60 places for every academic year, because we could run the course only on 2 quarters and not on every quarter of the year. And the demand has always been larger than 80 students, up to 100. So we had to implement waiting lists and selection criteria for students, which of course, in an ideal case, we would not want to, because we would like all students that want to take the course to be able to do it. On top of that, one of our other problems was the demand on the teaching staff for this course, because to run this course, we require always teaching assistants in the lab. And in a normal quarter, we will run 4 sessions per week. And each session required 3 to 4 TAs to be present for the half a day to assist the students. So that required teaching assistants to be busy half of their week just on this course. And moreover, from the correction side, so students that take this course as for most laboratory courses, were supposed to write reports. And then PhD and postdocs in our group were normally correcting them, but since we had 6 different experiments for this course, we had 6 different PhDs and postdocs taking care of this. And for them, it was quite burdensome because it could take up to 2 days for every week of the quarter, just correcting and meeting with the students. So there was quite a high load on our teaching staff. So our solution was to develop the virtual laboratory course. And this immediately offers some advantages. So we finally were able to offer enough places to all the students that demanded to or wanted to take the course. An additional advantage that immediately presented itself was a flexible schedule, because in the on-campus course, every student or at a specific time slot we were supposed to show up in the lab and carry out the experiment. Well, by moving the course online, we could dedicate an entire week to an experiment, and so the student could pick the best time for him or her to carry out the experiment. And so this allowed more flexibility also, especially for students that could decide the best time to do the job, let's say. And finally, there was a clear reduction in the stress on our teaching staff, because by moving the course online, we didn't require assistance in the lab. And also we took this opportunity to remove the report writing assessment and move to a more automated assessment, which of course is less demanding on teaching staff. However, a few challenges also immediately appeared and needed to be addressed by the development of this course. And first is student engagement. We needed to ensure that by not having students in the lab, but at home in front of their computer, they were still engaged and were still actively participating in the course, and they were not maybe getting more distracted, as is probably more common in this online education environment. And finally, we need to ensure that the learning objectives of the course could still be met by moving the course online, because of course it's a different environment. So the same learning objectives were not needed to be adapted maybe, but also we needed to ensure that even if the course was in a different environment, we could still meet the learning objectives. And just a couple of examples of learning objectives in a real laboratory course could be students making mistakes. That is for us a crucial part of a lab experience, and a student that maybe making wrong connection with cables and or making other type of mistakes in the lab from which they can learn, and something that maybe in an online environment is less easy to implement. And another learning objective or way they can learn more from a real laboratory is that the data that they measure or obtain is not as smooth as they're used to, because for most of the students, this is the first lab course they take. And before then, they were used to study the theory of a topic. So they're used to smooth curves and well-defined functions for the data they play with. And in a real lab course, it's not always like that. You get more noise in your measurement, and you get other sources of uncertainty. So that's something that is important in a real lab course, and we try to keep as much as possible. So when we moved this course online. So to go into the development, we'll start with the preliminary phase. So the first thing we needed to do, and actually in our case we didn't need to do, is design the course itself and the experiment. So as I mentioned, we had already a course which used to take place in a lab, and we needed to move it online. So that meant that we had already a lot of material, and we just, quote unquote, needed to move it online. But what I'm gonna say later, I think, can also be applied if any of you or anybody is interested in developing a laboratory course from scratch and wants to do it online immediately. Then everything I will say still applies, I believe, but then you will need to start from this to design first the course, because that is the first step, necessary first step, because you design, you have a series of learning objectives you want to achieve, and based on that you design the course, and only then you start really doing the nitty-gritty job of doing the online, or creating the online course, let's say. And after that, another crucial aspect that I found was that you need to meet with the developers of the virtual application, because of course, being this a virtual laboratory, you need somebody to create this virtual environment. And in our case, we selected the team at the VR Zone, which is, I think, is part of the New Media Center, but anyway, they work based on the library of the campus at the TU. And so we got in touch with them, and before we started doing anything, we needed at least a couple of meetings, let's say, on our side at the PVMD, to really tell them what we wanted to do, how our lab looks like, and what we wanted to obtain from the virtual application. And they start to tell us what they think are some limits or things that maybe they cannot achieve as we wanted them, so we need maybe to adapt to the circumstances, let's say. And this is really critical, I believe. But once we've done that, we move to the development proper. And first thing you start do is really take the developers and go with them to the lab and do the entire course. This is helpful for them because they may, or they usually are not familiar with the topic. For us, it's solar cells, so they are engineers that deal with computer science or programming, so it's quite a different topic. So they are not necessarily familiar with the topic itself. And most importantly, you do with them each of the tasks that students need to do in the laboratory, and they are the best person to tell you immediately if they think that, okay, we can do this task exactly identically as in real life, so there's no need to adapt anything. And in some other cases, they might tell you, okay, this could be more complex or almost impossible to do in a virtual environment. So consider adapting this because otherwise may not be possible to do it, let's say. So it's important to be with them and do the task together with them, so that you identify immediately roadblocks or critical points that need to be addressed in the design of the tasks themselves, let's say. Later on is you need to prepare a lot of material, and I can show you some examples maybe here, because you need to send them a lot of data for each of the tasks. So this is an example of one of the documents I have prepared for them, in which you need to, or I wanted to, but I think it was the best way, was to introduce a bit the topic, give a bit of description, and then the bullet points is the list, is the series of actions that students need to take in the lab, and they need to create in the virtual application for students to be able to do. So let's see if I can now stop sharing my screen. I'll go back to the presentation. Oh, sorry. Okay. We're back at the presentation, I think. So this is also critical to not only send them all the data they need in the background, and this can be equations that the the virtual laboratory need to solve live to model the physics of the experiments that we're doing. But sometimes you need to send them a full set of data that they need to recall as results of the experiment. And I found out that you cannot just send all the data and have them figure out themselves what to do with it. But giving a description of what is fundamental, obviously. And some second, still in the development part, let's say, some observation I made immediately is that the first task, as I mentioned before, we had 6 tasks and we start working from the first one. And this by far takes the longest time than all the others because both parties are learning to do this while doing. But also the other critical part that you do during the first task is finalize the design or the aesthetical appearance of your application. And this is an example here how it looks like. And once you do that and you move to the other task, you find out immediately that they go much more quickly because materials can be reused and the design, as I mentioned, is pretty much fixed. So there's a lot of less work to do for the other task. And just to give you some numbers here, the development of this course took us around 8 months in total. And let's say 3 months were dedicated to task 1. And in the other 5 months, we carried out the other 5 tasks. And there was even the summer holidays in between. So it was much more quickly to do the following task once the first one was completed. So my recommendation also here is spend a bit more time at the beginning, make sure everything is as you like it, because then the rest will be much more quick. And finally, once the raw material is ready, of course, comes testing. And testing, as I found out, is done in 2 different ways. There's some testing that I did personally as a developer of the course to check that everything that we required, let's say, or we expected from the app was there. But very crucial, I found out, is to have also some fresh eyes look at the entire course. And this is the virtual laboratory application, but also the rest of the course, so the assessment, because they might see something that you as developer that have been busy on the course for months don't see anymore. And one of these things is how easy to use is the app, the platform, because for you, for me that I was working on the app for many months, it was easy and everything was intuitive how the different commands worked. But maybe somebody that came in and tested it said, okay, this can maybe be better because I don't find it too intuitive. So I think this is really important, because if you then offer a course to a medium to large audience, I would say, you need to make sure that everybody is able to use it without having to learn too much or having to spend too much time understanding how to use it. And finally, there was another aspect that is maybe important to note is we needed to regulate the access to the application. So we don't want the application is hosted on servers of the TU Delft, but we need to ensure that not everybody with the link can just go there and use it, because we run the risk of too many people using it and then crashing the server when students need to use it. So we find out a way together with the extension school to restrict access only from links coming from Brightspace, for example, or you can do the same from edX, the edX platform. So that even if you have the address and you type it in your address bar, it won't send you to the app. You will be blocked, and you need to really click on the link on Brightspace or edX, where only people that are subscribed to the course can see the link then. So that's I think is an important note if you ever were to develop such a course which requires a separate app from Brightspace or edX to the experiments. You need to regulate the access, I say. So this is all I wanted to say, and now I would like to show a little bit the virtual laboratory itself, so that you might get an idea of how it looks like. So I'll share my screen again, and you should now see my browser, and this is the web application. So I'll go full screen. Can maybe somebody confirm me if they can see it properly?
Yeah, we can see it. Looks great.
Okay. So this is an example of one of the experiments that our students need to do. And just, I mean, here you have the title of the task, so they always remember, you always remember where you are. Here you can move between different parts to the next part of the experiment, or you can restart if you made a mess and you just want to start from point 0. You can just go here, and the main menu sends you back to the landing page. And here are a few commands. I will go through them very quickly. And important here, we decided to embed instructions here on the right-hand side to guide the students through. We also have a PDF guide, which was based on the guides that the students had in the real laboratory. But we found it best to have instruction embedded here because it makes everything easier for students. So this task, I have now to gently lay the probe station down on the table. So I can just click it on the probe station, and I will turn upside down. And once I do the command correctly, I can go to the next part, because if I don't do, I get a warning that I need to first execute the command before moving to the next part. And this is the way we can let students know when they made a mistake or not. So right now I need to just place the photodiode at the bottom of the probe station. This is the photodiode. When I hover over an element, a name of the element appears. So this is the photodiode. And once I click on it, in yellow appears the spot where I need to place it. So I just place it here. So then I can move to the next phase. I need to connect it to the photodiode to the supply. This is the power supply, and there are a few numbers here, 1, 2, 3. This is output 1, 2, and 3 of the supply, and I need to connect it to output 1. And this connection was actually one of, for the developers, was one of the tricky part, modeling these cables. It's not as easy as one may think. Maybe somebody that does programming knows better than me that this is quite hard, but I didn't imagine it was going to be this hard. But they did a really good job in creating this 3D cable model, which is basically elastic, so that you can stretch the cable as much as you want. And now I'm connecting it to the sockets here on the photodiode and to the sockets on the power supply, so that I'm actually can provide power to the photodiode. So I need to set the station upright again. So now I set it upright. I can move to this next step. And now this is output 1. This is the command. In the real life, the commands are here. And these two knobs here on the power supply, but it was not easy to incorporate them in this in the 3D object itself. So we gave this control panel here on the left-hand side, where you can control the command. In this case, we only need to control the voltage provided, so the current knob is deactivated. So I need to set the voltage to 5 volts. So I just need to click on the knob and turn it until I reach 5 volts. And if I click on the central part, I have the fine coarse adjustment, so I can be much more precise with my selection. So this is 5 volts. And I'm done. So now I can turn on. Next step is turning on the power supply. This is just providing voltage to the photodiode. And in this case, just to tell you a bit about what's going on in the background, actually we are using the equations here for the photodiode. So based on the voltage that we provide, the photodiode will respond slightly different. So we have some physical equation running in the background once you turn this on that define the response of the photodiode. So I can move to the next phase. I can now place the white LED, which is this one. I can, again, once you have to drag and drop something, the place where you have to drop it appears to help students know where to place it, the object. So now I placed it, and I need I can move to the next part. I need again to connect it, this time to output 2. And again, the sockets are here on the side. So I will connect them to output 2. And something I didn't mention, these sockets are colored because there's a positive and negative pole to each of these connections, obviously. And unfortunately, this is something that we couldn't really take over from real life, because in real life, if you swap the connection positive to negative, nothing really happens except that if you measure a quantity like current or voltage, you will get it negative or positive depending on the connection. Here we had to we couldn't implement this functionality, let's say, so we had to, if students connect the wrong polarity, they get a warning message and they need to invert the polarity before they can move on. Now I need to set the current provided to the LED to 700 milliamps. And again, here we have equation in the background, and depending on the current, we regulate the brightness of the LED, as you can see now, because if I turn on the LED, you will see light is shining from the LED on the photodiode, which is here. And if I increase the current, it gets a bit brighter until you exceed the maximum current of the LED, and then security kicks in and it switches off. So I need again to keep it at 700, otherwise it won't let me move on. And then what we need to do here is to find the right position of the LED so that the light that the LED shines on the photodiode is exactly the number we want. And the number is here. This is the current of the photodiode, which basically generates a current as response to being illuminated by light. And we need this value to be exactly 1.14, because that actually corresponds to the value that the photodiode will show if it was exposed to actual sunlight, let's say in a bright day. So we needed the same conditions here. So if I move it, you see I move the slider, the photodiode moves closer or further away, and I need to bring it around 10 centimeters to get the right response. And once this value is achieved, you can move to the next phase. And okay, this was the first example, and the task is much longer itself. I don't want to bore you much longer with it, so I stop presenting and I'll go back to conclude my presentation. So you should now see my slides again. Here. Okay. So to conclude, I summarize a few things, lessons, I call them, that we learned while developing and running the course. And I want to share them with you because they may be useful as if anybody's interested in creating their own virtual laboratory course. So the first thing, expectation can be subverted, which is a bit cryptic as a sentence, but what I meant here is that while working with the developers of the applications, there were some things that I thought were going to be very hard for them to carry out, and in the end they managed to do very quickly. Like, for example, including equations or large sets of data in the app for the results of the experiments, and that was actually very easy for them to do. Well, maybe I expected it to be much harder. On the other hand, other things that I thought were going to be much easier proved to be much more difficult or time consuming. For example, creating the 3D objects themselves that you saw in the application. I thought that the developers came to the lab while doing the experiments and took pictures of the various instruments. And I thought that, okay, once you have the picture, it's pretty easy to create a 3D object, but that actually was probably the longest task for them to do. So in this sense, be prepared maybe for things that you think are simple to take longer, and for other things that you may think are difficult to be much quicker. On the other hand, strong communication is, especially at the beginning, is key. I found that the guys at the VR zone very available, and that was really important because we're constantly communicating via email mostly about when we spotted problems or where things were not going maybe as we predicted, and that ensured that we were able to develop the course in time, because original plan for us was probably to release this course as a ProFed January of this year. But due to the pandemic, we anticipated it to be released in Q2 also for our TU students. So we had to finish the development 2 months earlier than we initially thought. But thanks to this communication from the beginning, that was actually not a huge problem. We managed quite easily to accelerate the development. And while running the course, a few things that I can share, although we only run it twice now because Q3 is almost finishing. A few things we already learned, like I mentioned at the beginning that the flexible schedule is a plus. On the other hand, still creating some sort of structure is also helpful. And what we did was in the time slots that in the original timetable were to be dedicated to the lab sessions in the lab, which were obviously not taking place, we decided that one teaching assistant would be available on Brightspace, on the virtual classroom environment, to answer questions for students. So by doing this, I found out that a big part of students then started actually doing the experiments in the original allotted time for the on-campus course, so that they got the chance to directly ask questions in the chat or with the microphone to me, rather than writing an email at a later stage, let's say. So that was beneficial for many students. But the second part is clarity of experiment guides. You saw that we had instructions embedded in the application, which most students actually praised and said that they were very clear and they helped them more than the PDF guides that we had prepared. And this is in contrast with another course we developed, another virtual laboratory course that we developed in parallel with another company, not the VR zone. And in that case, we didn't manage to include instructions in the virtual application, but we only had the PDF guide, and students sometimes complained that they were not as clear as they could have or should have been. So it's really crucial to have clear guides. And final observation about the results of the course. We found out that the passing rate is slightly higher, and grades are also slightly higher than in the previous years. And this, I think, has mostly to do with the assessment that moved from report writing or open question answering to closed questions that are answered online. So this, I think, is an important note to consider. I didn't speak too much about the assessment here because I think it was less interesting than the virtual application itself. But it's something that's really important to consider. So with this, that's all I wanted to say, and I'd like to thank you for your attention.
All right, thanks for the presentation. Now, if anyone has questions, you can either add them into the chat. And actually, it might be nice also to, if someone has questions on the demo and they wanted to see anything, we can always pull that back up if needed. I will say I tried out working in there, and I could only get through some of the tasks, I think, in the first course for the, like task 1 and 2. After that, I tried out just to see if it was functioning, and I couldn't even figure it out because it was way above my skills. But it was really nice to see. And I'm sure if I had like followed all the steps and with the guide, I probably would have done it. But I just tried to wing it and just check. It's definitely not one that you can just wing and try out. You definitely need to know a little bit about it, which is great. So it looks like we have one question here of what course did you use it in?
Okay, yeah, I didn't mention it clearly, but this was for the virtual, for the photovoltaic laboratory course, which is a course that we run in the AV faculty for many years now. And used to be an elective, and now it's within the SET program, which is a Sustainable Energy Technology Master program. If students want to do take the solar profile, they need to take this course. It's mandatory, together with other courses on solar energy that they usually do before this, so that they have the necessary background to understand the various experiments. So yeah, it's a master level course, and that I think is important because it requires some previous knowledge of the topic. And we also offered it as a ProFed, so a professional education course for people working in the solar energy field. But it was always recommended to these professionals that they took our other courses before this. We have other courses on theory and on modeling. And indeed, I was supervising the first run of this course, of this ProFed course, and all the participants, all the learners there were professionals that before this took our other courses, because it is not an entry course into the photovoltaic world, let's say.
And it looks like we have one more question here. How did the students experience it?
Okay, so this is very interesting because it's also probably the thing we were most curious about, because obviously, yeah, in an ideal world, we would want all the students to come to the lab and test this, play with the equipment themselves. But most students found it still very interesting. Not still, they found it really interesting, and they say that it looked really realistic. So the experience with the various components, cables, light sources, solar cells, other electronic components. Sorry, they found it really not lifelike, obviously, but really similar to real life. So that they thought that it was really nice done, especially in consideration of the time that passed between then when there was no course, they couldn't just do the course, and now they have at least an alternative to going to the lab, which is not possible at the moment. We also had some feedback from our beta tester, which were luckily for us students that did the course in the lab in past years, and from them, so they could do the proper comparison between the real life course and the virtual course. They found it very similar, and they thought that the learning objectives or whatever you would learn from real life, the real life course was well translated to the virtual environment. I hope this answer the question.
Yeah, thanks. If you have any other questions, feel free to use your microphone or your camera, or add it to the chat here. And if you had questions specifically about the demo, maybe let us know too. Looks like we have one more question of were there a lot of students asking for guidance, and what did you use for communication while they were working in the lab, only Brightspace discussions or other channels as well?
Okay, here I think I need to make a distinction between this course I've shown you and our other course, which I didn't show you because I think it's really similar in many ways. So it only made sense to show one of the courses. But the big difference is this virtual photovoltaic laboratory course is a master level course, and the other course was a bachelor level. So it's a minor for bachelor students of electrical engineering. And my experience, since I was, let's say, supervising both courses, is that bachelor students need more guidance. And as I mentioned, twice a week for 4 hours at a time, I was available live on Brightspace using the virtual classroom environment, so they could just turn on the mic and ask me questions or write them in the chat. The discussion on Brightspace was, of course, available, and that was the main way used by the master course, the photovoltaic laboratory course. They mostly ask questions on the discussion, and other students were also answering questions of their colleagues, while in the bachelor level, they mostly waited for me to provide an answer. That at least was my experience. And I always mentioned that outside, let's say, normal hours, it was quicker if they were just wrote me an email with questions, because I was checking the discussion on Brightspace maybe once a day. So if they needed more urgent support, they could write me an email. I would usually answering within the hour, let's say. So these are the ways that I was using.
Great. I actually have one question myself. For the students who actually finished this course and had used the online resource, did you have a chance yet to see any of those students in the lab in person yet, to see how they are interacting now in the in-person lab? Because I'm just kind of curious to see if, if they did the online part and then they're in the lab, do you see a difference where you would say, wow, they still have a huge gap, they missed something in the online course, or they're clearly doing awesome, they know what they're doing, and there's no difference from as if I had that been on campus before?
No, I have not had the chance, and that actually is a very interesting point that you bring up, because in our original plan, that when we developed this course was, yeah, we would like to offer this to all our students. They can take the virtual course, and then at some point have them all come to the real lab and try try something. By try something, and I mean probably that instead of doing all 6 tasks in the lab, they could maybe do one just to get the feel of it, but then they do the other 5, let's say all 6 online. In that way, they get the feeling for the real life thing, and it also helps them then connecting with the other tasks that they only do virtually. At the moment, it was not possible yet. I don't have direct experience of any of the students that may have started doing a thesis with us. They might have then start going to the lab. So I don't know if the supervisors experienced a gap in their ability to work in the lab now that they have never been there before, with respect to years past when they started a thesis with us. They all have done the PV lab course in the lab, so they at least have some manual experience on how to work in the lab. So I don't have data for that, but it's something that we could I need to check if any of the students that took the course already started the thesis, which might be possible, and then maybe we can ask supervisors if they saw that they are less good in the lab than they were before. Although the laboratory work for this course and for a thesis is quite different also. So there's a bit of overlap, but not too much also, I would say.
Great. No, I was just kind of curious. Any other questions, or did anyone else want to see anything further in the demo? Are any of you thinking about using something like this in a future course yourself? Just kind of curious what you think now that you've seen this demo, what you might think about for a future course or future thing in your in a program or anything like that.
There is something I want to mention again, because what I've shown you is the translation of an existing course to the online environment, which is what we were interested in doing right now. That was very simply what we wanted to do. But I think there should not be a limit. And in particular, we are already thinking of expanding our virtual laboratory courses to do tasks or experiments that in the real lab would not be possible. For example, as we play with solar energy, in the lab, students will work with small solar cells, or maybe some of the PV modules, which, I mean, they are big, but one can carry by hand, let's say. So there's still stuff that can be hosted in a university laboratory. We are already thinking of having the students do virtual experiments on power plants. So maybe where you have hundreds or even thousands of these PV modules, and you need to connect them, maybe not all of them manually, but decide how to place them, how to connect them, which equipment to select for this power plant. So you can think of doing experiments and in real life would not be possible, let's say. So I think this is where we would move beyond just translating an existing laboratory course into a virtual one, but actually taking advantage of the extra possibilities that virtual environment offers. So I think this should also be taken into account if anybody is interested in developing a virtual laboratory course.
All right, thanks. It does look very exciting, and I can't imagine this year particularly. It's probably very nice to have for the students who can't go to campus. So it's probably been a really help this past year. Nice. Well, if there's not any other questions, I can actually let you know what next week we have. Next week we have the open discussion and Q&A on anything related to remote teaching and learning. So I'll post that here. So that's next week. So it's just a general questions that you might have. You can also come and talk about any successes that you have. So if something's going really well for you, come and share how something is happening for you. So please let us know. And that'll be for next week. I'll go ahead and end the recording. And thank you for joining us, for those of you that are watching.